Okay, we're going to talk about the material from lecture 11. This lecture is on counting stuff, which sounds strange, but you'll see. I need to say, of course, that this video is no substitute for reading the book and notes. Those are primary, this is supplemental. Okay, well, the reason we need to talk about counting is because lots of times in probability problems we have a sample space with lots of equally likely outcomes, and then you remember the probability of an event, E, is just the number of outcomes in E divided by the number of outcomes in the whole sample space. Right? Well, in order to compute probabilities then, we need to be able to count these things. It's simple enough to count them when you're just talking about rolling a couple of dice or something, but think about even something like dealing a 5-card hand out of a standard deck. Right? There are an awful lot of ways you can do that, an awful lot of things there, and learning to count things in that kind of situation is the sort of thing we need. All right, we're going to have a few techniques. The simplest, the most straightforward of them is called the fundamental counting principle. Right? Which here I'm just going to abbreviate FCP. It's also called the multiplication rule many times, and it's very simple. It says if you have 2 tasks to do, 2 tasks, say numbers 1 and 2, and there are m ways to do task 1 and n ways to do task 2, then there are m times n ways to do first task 1, then task 2. And this actually extends to any number of tasks. Right? If you had a task 3 with, say, r ways to do task 3, then there would be m times n times r ways to do first 1, then 2, then task number 3, and so on and so forth. Doesn't really matter how many. Okay, let's take a look at a simple problem like this. Simple problem that uses this. A couple of them. The Wednesday special at Meatza Pizza is a 1-person pizza with 1 topping and a soft drink for $8.95. If there are 12 different toppings to choose from and 6 different soft drinks, how many different Wednesday specials can be ordered? Okay, well, we think of the problem of counting the number of possible Wednesday specials as being the same as counting the number of ways in which we could choose such a special. And we think of choosing a Wednesday special as being broken down into 2 tasks. So first we can choose a topping, and then we can choose a drink. And there are 12 ways to choose a topping, and there are 6 ways to choose a drink. So there are going to be 12 times 6, or 72 ways to choose first a topping and then a drink. And so there are going to be 72 possible Wednesday specials. Let me show you a little shorthand way in which people write this sometimes. They think of having a kind of a slot for each task. So this slot would represent choose a topping, and this one would represent choose a drink, And then you fill in these slots with the number of ways to do each task. There are 12 ways to do the first task and 6 ways to do the second. 12 times 6 is 72. Lots of times you'll see that sort of shorthand way of writing it. Okay, here's a similar problem. At Lisa's Pizza, the Thursday special is a large pizza with any combination of toppings, but no more than one of each. The available toppings are pepperoni, mushrooms, onions, sausage, peppers, olives, and pineapple. How many different Thursday specials can be all ordered? I'm going to think of, first of all, the process of ordering a Thursday special as being made up of 7 different tasks. The tasks are choose to have pepperoni or not. Second task would be choose to have mushrooms or not, and so on all the way down to choose to have pineapple or not. I don't have any idea why anyone would choose to have pineapple on a pizza, but okay. Right, so that would give me 7 different slots. Right, the first one would correspond to choose whether to have pepperoni or not. Second one would be choose to have mushrooms, choose to have onions, and so on, all the way down to choose to have pineapple. And how many ways are there for each of these tasks? How many ways are there to accomplish it, so to speak? Well, you can only either have pepperoni or not have pepperoni. Right? So there are going to be 2 ways to do that task. 2 ways to complete the task of choosing mushrooms or not. And similarly for all the rest. Right? 2 ways each. And so what you end up with here is 2 times 2 times 2, and so on all the way down to here. There are 7 of them, so that's 2 to the 7th, which happens to be 128. All right. The next thing we're going to look at is called permutations. And for permutations, you think of having some objects, n objects in general, but some number of objects, and you're going to choose an ordering of them, or going to choose them in order, whichever way you prefer to say it. Right? And that's what a permutation is. A permutation of n objects is an arrangement of them. In a particular order. Right? It's important to remember that order matters when you're talking about permutations. You're really talking about choosing an order. Right? So if the objects are, let's say, this, and that, then how many different ways could you order those? Well, you could have plus, you could have this order right here, times plus circle box, let's say, or you could have times plus box circle, or you could have, well, it turns out there are a whole lot of them. And we'd be interested to know how many ways there are to choose a permutation of 4 objects like this. But that's what we want to know, this very generally. How many permutations are there of n objects? Well, we can think of choosing a permutation. Let's just stick to these 4 for the moment. We can think of having 4 slots. Right? Whatever permutation you end up with, it corresponds to putting one of these objects in each slot. And we think of this as corresponding to 4 tasks. Right? We're going to choose a first symbol, and then a second symbol, and then a third, and then finally the last one. Now there are 4 different symbols. They have to be different, or this doesn't work. This is for distinct objects. There are 4 different symbols, so when I go to fill in the first slot here, I get 4 ways to do that. Remember, I'm putting in the number of ways to choose in each slot. When I go to fill in the second slot, I've used up one of the symbols. Whichever one I chose, it's used up. I can't use it again, so I only get 3 ways to choose that second symbol. And then 2 ways for the third and 1 for the last. So this would be 4 times 3 times 2 times 1. which is 24. We write this 4 with an exclamation point for that number, 4 times 3 times 2 times 1. This is called 4 factorial. And you can use that exclamation point factorial symbol with anything, like, 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. In general, n factorial is all the numbers, all the integers from 1 to n, all multiplied together. Okay, we're going to push this just a little farther. Suppose I had 5 objects. Let's start with these guys. And, I don't know, diamond. Okay, I have 5 objects. And I have a box with 3 slots in it. And I think of these as being ordered from left to right. What I want to do is I want to choose 3 of these 5 symbols to put in the box. And the order matters. When I go to choose something for the first slot here, I get 5 ways to choose. And then for the second slot, I get 4. And for the third, I get 3. So they're going to be 5 times 4 times 3 possible results. When you do this, when you choose like 3 objects out of a set of 5 in a definite order, where the objects are all distinct and you can't choose any object more than once, right? That's called a permutation of, well, I'm going to write it generally, that's called a permutation of 3 objects chosen from among 5. But in general, you can have a permutation of R objects chosen from among N objects, and that is a selection of the R objects in a particular order. It's just a slight generalization of the thing we started out with. And the number, this is the thing we're interested in here, the number of permutations of R objects chosen from among N is, well, one notation for it is P of NR, R, P of NR, and the number is N factorial over N minus R factorial. That can also be written this way, N, a little subscribed N, and then a P, and a little subscribed R. This is the way your calculator will write it. Okay. Let's see. Here's a simple problem that involves these things. 12 horses are running in a race. How many different first, second, and third place winners are possible? Well, I can think of this as choosing 3 horses in order, or I can think of choosing 3 horses and then ordering them. I don't care which way you think about it, as long as you understand that in the end, it matters what order they're in. Right? Order matters in this problem. So, order matters. I'm choosing 3 items, in this case horses, from among 12 in a particular order. So the number of ways to do that is going to be P of 12, 3, which is 12 factorial over 12 minus 3 factorial. Okay. You could also do this problem without thinking about permutations at all in particular. Right? You could simply do it by the fundamental counting principle, and that's often the case for these simple problems. You could think of picking a first place winner, a second place winner, which is called place, and a third place winner, which is called show, right? Win, place, show. There are 12 horses here. One of them is going to win, but any one of them can win, so we'll get 12 ways to choose a winner. But the same horse can't both win and place, So we'd have to choose a different one. We'll have 11 to choose from, so there will be 11 ways to do that, and then 10 ways to pick a horse to show. So this would be 12 times 11 times 10. And those are the same number. Okay. So we have the fundamental counting principle, and we have permutations. We need to talk about combinations. A combination of R objects chosen from among n, no, set of n objects, is a selection of R objects without regard to order. A combination is just choosing R objects to throw in a sack. Right? There's no possible way the order can matter. And we're interested, of course, in the number of combinations of R objects chosen from among n. That is denoted C of nr, and the formula for it is n factorial over n minus r factorial times r factorial. It looks a lot like the formula for p of n and r, except there's this extra factor down in the denominator here, r factorial. Okay, let me do a quick example of such a thing. Let's suppose that a restaurant allows a choice of 3 side dishes when a customer orders an entree. Okay. And if they have, let's say, 12 side dishes to choose from, how many different choices can be made? How many different choices of side dishes can be made? Well, the question here is, does order matter? Well, you already know it doesn't because of where I'm talking about this, but if this were in the homework or on a test, you'd have to think. Does order matter? Well, if you order the green beans, the peas, and the mashed potatoes, or you order the mashed potatoes and then the green beans and then the peas, do you get a different meal? You don't, right? The end result does not matter. That does not depend on the order in any way. And after you choose, you're not going to be ordering them. In fact, if the waitress brings you your entree and 3 side dishes, you can move those side dishes around into any order you like. Right? There's no way order matters here. And so this is going to be a choice of 3 items from among 12 where order doesn't matter. Right? It's only what items are chosen, not the order. And in this case, then, there are going to be C of 12, 3 different choices. Okay. When the numbers get large, C of 12, 3 is pretty easy to compute. I might as well just go ahead and do one here. 12 factorial over 12 minus 3 factorial, 3 factorial. So this is 12 factorial over 9 factorial, 3 factorial. And remember what 12 factorial is. So let me write this. I'm not going to write the whole thing, but 12 times 11 times 10, times 9, times 8, times 7, and so on, all the way down to times 2 times 1. That's 12 factorial in the numerator there. What's the denominator? Well, it's 9 times 8 times 7, and so on, all the way down to times 1. And then times 3 factorial, which is 3 times 2 times 1. And you can see that there's a whole lot of cancellation here. This big product, 9 down to 1, all cancels with this big product. So you end up with 12 times 11 times 10 over 3 times 2 times 1. And I can do that in my head, right? This is 2 times 11 times 10, which is 220. So it's not hard to compute these things when the numbers are small. When the numbers get larger, it is harder to compute, and then you should use your calculator. And there's a video in the book that shows you how to do that. Shows you how to find factorials, shows you how to find the number of permutations or combinations, the P of NR or C of NR. And so I won't do that here. What I do want to do is a few more problems. I want to say counting problems can be quite difficult. And I cannot give you any hard and fast rules as to how they should be approached. But I can give you some kind of guidelines. First thing you need to do is ask yourself two questions. First, ask, is it possible to choose any item twice? When you're picking horses for win, place, and show, you can't choose any horse twice. Right? In lots of these examples, you haven't been able to choose anything twice. But think of a problem in which, for example, you were asked to pick the number, to find the number of 4-digit binary numbers. That is, each digit has to be 0 or 1. Right? Well, in this case, you can think of this as choosing digits from the set containing just 0 and 1. And this number, 0001, is a perfectly good 4-digit binary number. Right? And so is 1001 and so on. Right? So you have to be able to choose 0 as many times as you need to and 1 as many times as you need to. So in this case, it is possible to choose an item twice. And if the answer to this question is yes, then the only tool you have is the fundamental counting principle. It's not going to be permutations or combinations because those require distinct objects. They require objects you can tell the difference between, and they require that each one be chosen only once. Okay. Otherwise, if you can't choose any item twice, then you need to ask the second question, which is, does order matter? Right? Do you get a different result if the order in which things are chosen matters, or do you have to order things after they are chosen? If order does matter, then you should use either the fundamental counting principle or permutations. Okay? P of NR, that's what you're looking for. If no, then it's a C of NR kind of problem. And as I said, it's not easy. You just have to think hard about each problem. Okay, here are some examples. A club with 10 members must elect a president and a vice president. If no one can hold more than one office at a time, how many different choices could be made? So we have 10 people. Okay? We'll give them each a number. We'll call them 1 through 10. Each one of them will have a little number written on his forehead. And we're going to choose 2 of those people. And we have a little spot on the wall. Here it is. Right? A spot on the wall. And there's a tag marked president. And there's a tag marked vice president. Right? And we're going to choose the 2 people, and we're going to stand one of them underneath this sign. And we're going to stand the other one underneath this sign. If we put Alice here and Bob here, then Alice is president and Bob is vice president. But if we put them the other way around, then Bob is president and Alice is vice president. So the order matters here. Definitely order matters. We end up with a different result if we choose a different ordering. So this is going to be a P of 10, 2 kind of problem. All right, You could also think of this as a strict fundamental counting principle sort of problem, right? You could think of having two tasks, choose a president, and the second task would be choose a vice president. Excuse me. There are 10 ways to do the first task, and there are 9 ways to do the second task, so there are going to be 10 times 9, or 90 ways to do the two tasks together. And that, of course, is the same number as P of 10, too. Okay, here's a different sort of problem. A combination lock has 4 rotators, each of which contains the digits 0 through 9. How many different combinations are possible? Well, let's think about what a combination should look like. Right? A combination will be 4 numbers, right? One for the first rotator, one for the second, and so on. Well, what kind of things can combinations be? Well, for example, you could have a combination that looked like this: 1, 2, 8, 7. But you could also have a combination that looked like this: 1, 1, 3, 1. So you can reuse these digits. If you think of doing this by having the digits 0, 1, and so on up to 9, you can choose these things as many times as you need to make up a combination. So you can choose items more than once in this kind of problem. So the only thing you have to work with is the fundamental counting principle. So you should think of this as 4 different tasks, right? Choose a digit for the first rotator, choose a digit for the second rotator, and so on. Right? You'd have 10 ways to do the first task. Any of the 10 digits will do. Same with the second, same with the third, same with the fourth. And so you get 10 multiplied by itself 4 times, 10 to the fourth, which is 10,000. Okay. Finally, how many different 5-card draw poker hands can be dealt from a standard deck? In draw poker, you get 5 cards dealt to you. You can pick them up and you can rearrange them any way you want to. Right? So in this case, order doesn't matter. Order doesn't matter at all. The hand is the hand, regardless of the order in which you get it. And so it is C of 52, 5. And you can do that out on your calculator if you want to see the number. It's about 2.5 million. All right, that's about it for the counting section.